Hello there, and in this video we're going to continue our discussion for the radius of convergence for power series for functions. So we're going to first begin by reviewing what do we mean by the power series of functions. So we're going to assume that there exists this representation in the sum of ak times x minus a to the k. We're going to assume that this representation exists for f, so it has to satisfy its differentiability criteria. So we can find the radius of convergence r to be equal to the limit as k goes to infinity of ak divided by ak plus 1, and then we say the interval of convergence for this series is going to be equal to a minus r, a plus r. In this video we're going to work through a couple examples on how to calculate the interval of convergence for a power series and figure out whether you should include these boundary points or not. Alright, so for our first example, let us consider the following series. Suppose we have the series the sum from k is equal to 0 to infinity of 3 to the power 3k times x to the power 2k. So clearly, since this is our variable term, we see that the center of our interval will be a is equal to 0. So now we need to figure out for which values of x will this actually converge. So an, in this case, is going to be equal to 3 to the power 3m. An plus 1 is going to be equal to 3 to the power 3, n plus 1, or equivalently 3 to the power 3n times 3 to the power 3. So our radius of convergence, r, is going to be equal to the limit, as n goes to infinity, of an divided by an plus 1, the absolute value. Both an and an plus 1 are exponential functions, so they're both positive, so we can leave off the absolute value signs. So this is going to be equal to 3 to the 3n all over 3 to the 3m times 3 to the 3. Our exponential terms with n's cancel. So of course this is going to be equal to what? Well, let's not forget our limit. So limit as n goes to infinity, this expression. So there is no n's, so this is just going to be 1 divided by 27. So that means the interval of convergence is going to be of the form a minus r and a plus r. Here's r, and a is equal to 0. So that means I is going to be equal to the interval negative 1 over 27th comma 1 over 27. So now we need to see whether the endpoints plus or minus 1/27th converge or diverge. So let's first consider the left endpoint. So we're going to look at x is equal to negative 1 over 27th. So when x is equal to negative 1/27th, our series is the sum from k is equal to 0 to infinity of 3 to the power 3k times x negative 1 over 27 to the power 3k. So what exactly is this? So notice we have a negative sign inside of an odd power, so it alternates from positive to negative. So we can rewrite this as the sum from k is equal to 0 to infinity of negative 1 to the k times what? So we have 3 times 1 over 27th, the same power, so we can combine the insides. So that's going to be 3 over 27th, which is the same as 1 over 9. To the power 3k. So we can use our alternating series test and primarily focus on this last term. So this is always positive and always decreasing. So that means this converges. So that means the point negative 1 over 27th is an element of the interval of convergence. So now let's look at the right. So the right turns into the sum from k is equal to 0 to infinity of 3 to the 3k times positive 1 over 27th to the power 3k. So again, both 3 and 1/27 have the same exact exponent. So we can rewrite this as the sum from k is equal to 0 to infinity of 1/9 to the power 3k, which is the same as the sum from k is equal to 0 to infinity. So this is a power to a power in a way, so we can rewrite this as 1/9 cubed to the power k. So this number here is in between -1 and 1, so that means this converges by a geometric series test. So that means the point 1/27 is also an element of the interval of convergence. So therefore the interval for convergence is going to be equal to the closed interval -1/27 comma +1/27. So now let us look at another example to sort of illustrate this idea. So example 2. Consider the series, the sum from k is equal to 1 to infinity of 2 to the power k divided by k times x minus 5 raised to the kth power. So since this is a variable term, we can easily see that this power series is centered around the point 5. So that means our interval of convergence is going to be in the form 5 minus r, 5 plus r. And then we can test the boundaries to see if whether they're in the interval of convergence or not. So an, in this case, is going to be equal to 2 to the n all over m. n plus 1 is going to be equal to 2 to the n plus 1 over n plus 1, which is just the same thing as 2 to the n times 2 all over n plus 1. So that means the radius of convergence is going to be equal to the limit as n goes to infinity of the absolute value of 2 to the n over m divided by this term, or multiplied by the reciprocal of that term. So it's going to be n plus 1 all over 2 to the n times 2. As n is arbitrarily positive, all the terms, including n and n plus 1, are also positive as well. So the absolute value bars can be removed. We have 2 to the n, 2 to the n, those will cancel. So we have that r is going to be equal to the limit as n goes to infinity of n plus 1 all over 2n. So by L'Hopital's rule, one can verify that this is going to be equal to 1/2. So that means the interval of convergence is going to be equal to a minus 1/2, then a plus 1/2. So 5 minus 1/2 is the same as 10 halves minus 1/2, so that's going to be equal to 9 halves. And the other is just going to be a half above 10, so that's going to be 11 halves. So this is our generic interval of convergence. So now let us test our endpoints to the left and the right. So the left, we're going to test the point 9 halves. So if that is the case, our series is the sum from k is equal to 1 to infinity of 2 to the k all over k times 9 halves minus 5 to the power of k. So that's going to be equal to the sum from k is equal to 1 to infinity of 2 to the k over k times, so 9 halves minus 5, that's going to be -1/2 to the power k. So this is going to be an alternating series, so I'm going to write it in that form. So this is going to be the sum from k is equal to 1 to infinity of -1 to the k. And what is going to be my other term? Let's see. So if we look here, we have 2 to the k and 2 to the k as well. We've already isolated the negative ones, so those will cancel. And this is going to be equal to, so we still have this k on the bottom, so that's going to be 1 over k. So this is an alternating series test. Namely, it's an alternating harmonic series. So we already know that this is going to be equal to the natural log of 2. The alternating series tests say it converges anyway, so it really doesn't matter what this is. So that means that x is equal to 9 halves is an element of the interval of convergence. So now let's look at the right-hand side, namely the point x is equal to 11 halves. So if we look at the point 11 halves, we have the sum from k is equal to 1 to infinity of 2 to the k over k times 11 halves minus 5 to the power k. This is going to be equal to the sum from k is equal to 1 to infinity of 2 to the k all over k times, so 11 halves minus 5 is just going to be a positive half to the k. 2 to the k and 2 to the k will cancel. So this is going to be equal to the sum from k is equal to 1 to infinity of 1 over k. So we know that this is a harmonic series which diverges, which we can verify by the integral test, because the integral of 1 over x is natural log of x, which diverges as you go to infinity. So what does this mean? So this means 11 halves is not in the interval of convergence. So in conclusion, the interval of convergence is going to be equal to the half open interval, 9 halves, 11 halves. And this is how you can calculate the radius of convergence and also the interval of convergence for various power series, and also how to test the convergence of the series at the endpoints of the interval.